Hello my dear students, welcome back to your channel. Hope you all are doing well. Today I am going to start quick revision of chapter 13 of class 11th physics, that is kinetic theory of gases. In this chapter, different topics to be covered are first gas laws, then equation of a state of a perfect or ideal gas. After that, kinetic theory of gases. In this one we study about assumptions, then concept of pressure, then kinetic interpretation of temperature, RMS speed of gas molecules. After that, degrees of freedom, then law of equipartition of energy and application to specific heat capacities of gases. Then there is a very small topic, that is what is mean free path, and then Avogadro's number. This chapter is very small, and in this chapter we basically study about the molecules of gases. Actually, atoms or molecules are constantly in random motion in case of gas. So we basically study about kinetic theory of gases. In terms of molecular force of attraction between gas molecules is very small, like comparison to solids and liquids right now. So we only study about behavior of gases and their kinetic energy. So first we will start with what are different gas laws, and then equation of a state of a perfect gas. So what are different gas laws? First one is Boyle's law. What is the statement of this Boyle's law? At constant temperature, volume of a given mass of a gas is inversely proportional to pressure. Right, at constant temperature. It means PV is constant. For a given gas, P1 V1 is equal to P2 V2. If you draw a graph between pressure and volume, then if you increase the pressure, then volume decreases. Both are inversely proportional to each other. So this is the graph between P and this side V. And you know, if you draw a graph between pressure and 1 by V, so here it is clear that pressure is directly proportional to 1 by V. So graph between pressure and 1 by V is a straight line. Okay, hope it's clear to all of you. Next, second law is Charles law. What is the statement of this Charles law? At constant pressure, right? At constant pressure, this volume of a given mass of a gas is directly proportional to its temperature. It means V by T is constant. For a given gas, V1 by T1 is equal to V2 by T2. And if you draw a graph between volume and this side temperature, right, it is a directly relation. So it is a straight line. But at 0 degree centigrade, volume is not 0. It has some initial volume V0. It becomes 0 at this temperature, minus 273 degree Celsius. And the temperature at which volume becomes 0, this temperature is called absolute zero temperature. We already discussed in thermal properties of matter right now, or you can say 0 Kelvin. This is in degree Celsius, right? Next, third one is Gay-Lussac's law. What is the statement of this Gay-Lussac's law? At constant volume, pressure is directly proportional to temperature. It means P by T is constant. For a given gas, P1 by T1 equal to P2 by T2. This is the statement of Gay-Lussac's law. It means at constant volume, this side is pressure and this side is temperature, right? So this is direct relation. If P increases, temperature also increases, but at 0 degree Celsius, pressure is again not 0. It becomes 0 at this temperature, minus 273 degree Celsius. So this temperature is called absolute zero temperature. It means absolute zero temperature is those temperature at which molecular motion stops, volume and pressure becomes 0. And this is minus 273 degree Celsius or 0 Kelvin. This is absolute zero temperature. We already discussed in thermal properties of matter. Next, after this one, Avogadro's law. What is this Avogadro's law? Avogadro stated that equal volume of all gases, if there are number of gases, and equal volume of all gases under similar conditions of temperature and pressure contain equal number of molecules. This is a statement of Avogadro's hypothesis, right? If number of gases are there and volume of all the gases are same, then under similar conditions of temperature and pressure, it contains equal number of molecules, right? So these are different gas laws. After that, next is perfect or ideal gas equation. First, what do you mean by this ideal gas? Gases which obeys all gas laws in all conditions of pressure and temperature are called perfect or ideal gas. And perfect gas equation or ideal gas equation is given by PV equal to nRT. P is pressure, V is volume, N is number of moles of a gas, R is universal gas constant, and T is absolute temperature. The value of this universal gas constant is R equal to 8.31 in joule per mole per Kelvin. Now, how you get this equation? This question is also very important. Derivation of ideal gas equation. You have to combine all gas laws, you get this equation, because ideal gases are those gases which obeys all gas laws in all conditions of pressure and temperature. So first I am going to derive this one. First, according to Boyle's law, V is inversely proportional to pressure. According to Charles' law, V is directly proportional to temperature, and according to Avogadro's law, equal volume of all gases contains equal number of molecules. So V is directly proportional to N. If you combine all these three equations, you get V is directly proportional to NTP, or you can say PV is equal to, V is directly proportional to NT by P. Right now, so PV is directly proportional to NT, or you can say PV equal to NT, and this is proportionally constant, that is called universal gas constant R, and its value is 8.31 joule per mole per Kelvin. So in this way you derive this equation, ideal gas equation, PV equal to nRT, right? You have to use different gas laws, you combine all these laws, you get this equation, right? After this, next is how you get the value of this R, 8.315 joule per mole per Kelvin. You know, ideal gas equation is what? PV equal to nRT. From here, R becomes PV by NT. For 1 mole of a gas at a standard temperature pressure, P is 1 atmosphere, volume is 22.4 liter, and temperature is 273 degree Kelvin, right? For 1 mole at a standard temperature pressure. You put all these values, you get R equal to 8.315 joule per mole per Kelvin. In this way, you calculate the value of R. Now, next, different forms of perfect gas equation. You know, gas equation is what? PV equal to nRT. This is one form of ideal or perfect gas equation. You can write in another way also. First one is in terms of number of moles, right? Then mass and molecular mass of the gas. You know, number of moles is defined as what? Mass of gas by molecular weight of gas. It means N equal to M by M naught. M is mass of a gas and M naught is molecular mass of the gas. For perfect gas equation, you know PV equal to nRT. You put the value of number of moles N, M by M naught. You get P equal to, you write V in the denominator here. So you take M by V one side together, RT by M naught. This M by V is what? Mass per unit volume is density. So you can write rho RT by M naught. So P equal to rho RT by M naught. M naught is molecular weight of the gas. Rho is density of the gas. So this is one form of perfect gas equation in terms of density. P equal to rho RT by M naught, right? You can also write number of moles in terms of Avogadro number right now. So Avogadro number of moles is number of molecules divided by Avogadro number, right? So N equal to N, number of molecules is N, and Na is Avogadro number. You know Avogadro number right now. So PV equal to nRT, you write in place of N, N by Na. N is total number of molecules, Na is Avogadro number, right? So you can write PV equal to N, this R by Na, you take R by Na together into T, and this R by Na, you can write this R by Na, it means universal gas constant by Avogadro number, as Kb. Kb is called Boltzmann's constant, and its value is given by 1.38 into 10 to the minus 23 joule per mole Kelvin, right? So PV becomes NKBT, or you can write P equal to, take V in the denominator, NKB by Vt, and you know N by V is what? N by V is number density, right? Number density. So you can write P equal to N KBT. Small n is number density, number of moles per unit volume. So this is in terms of Boltzmann's constant, P equal to N KBT, or you can write P equal to N KB by Vt, right? This Kb is Boltzmann's constant. So these are two different forms of perfect gas equation. You must know how to write in this form, okay? After this, there is a graph between ideal gas and real gas, right? So first, what is this ideal gas and real gases? Actually, this ideal gas is purely theoretical. At what is ideal gas? At all pressure and temperature, a gas that exactly fulfills the perfect gas equation PV equal to nRT are called ideal gas. Here, the concept of this ideal gas is purely theoretical. There is no intermolecular force of attraction between molecules. If these conditions exist, then that type of gas is called ideal gas. But in reality, gas molecules always attract one another. These are real gases, and real gas molecules occupy a finite volume. So, but there is one condition: for low pressure and high temperature, this real gas approaches ideal gas behavior. How you draw a graph between this ideal gas and real gas? Okay, you know perfect gas equation is what? PV equal to nRT, or you can write PV by RT is constant. PV by RT is constant. This is equation for ideal gas. It means PV by RT, if you draw along y axis PV by RT, and along this x axis pressure is there. So PV by RT is constant for ideal gas. This is the graph for ideal gas, right? Now at low pressure, these are low pressure, and when you increase the pressure and also when you increase the temperature, this one is for low temperature, graph is this one. This first is for low temperature. Again, your temperature increases, you get graph like this one. Again, you increase the temperature, you get graph like this one. And this at higher temperature, this one, and at low pressure, this graph is similar to ideal gas. So from this equation, why this so happen at high temperature? Actually, what happens at high temperature, molecules are far apart right now. So when the temperature is raised, the molecules will randomly move away from each other, and it satisfy the condition of ideal gas where there is no intermolecular force of attraction. So as a result, intermolecular interaction decreases and the gas acts like an ideal gas. So from the graph, it is clear that at low pressure, high temperature, these two are important conditions. These real gases approaches the ideal gas behavior, right? After this, next topic is kinetic theory of gases. Very important topic, right? Kinetic theory of gases. There are different assumptions of kinetic theory of gases. First one is, all these points are very important. First point is, all gases consist of extremely small particles known as molecules, and the molecules of a given gas are all identical but are different from those of another gas. For the same gas, all the molecules are identical. Now, second one, the shape of the molecule is always spherical. Then third, important, the molecules of a gas are constantly in random motion along a straight line, right? The molecules are always in random motion, it always moves along a straight line. It means there is no gravitational force acts on these molecules. Next, fourth one is, the size of the molecules is negligible as compared to distance between them. The size of molecules is very small as compared to distance between the two molecules. Also, during their random motion, molecules collide with one another and also with the walls of the container, right? And these collisions are perfectly elastic. It means there is no force of attraction or repulsion between the gas molecules. Next, these collisions are almost instantaneous. It takes place very instantly, randomly, very fast. Next point is, between two collision molecules always moves in a straight line with uniform velocity, right? And next important point is, the distance covered by the molecules between two successive collisions is known as free path, and the average of all these free paths is known as mean free path, right? And next important point is, assumption is, the density remains uniform throughout the gas, and all gas molecules moves along a straight line, so gravity is neglected due to its small masses and very high speed of molecules. So on the basis of these assumptions of kinetic theory of gases, next important topic is how you derive pressure of ideal gas, right? So next topic is pressure of an ideal gas based on kinetic theory of gases. So you know, a gas exerts pressure due to its continuous collision of its molecules with these walls of the container right now, and it bounces back, and due to this there is a change in momentum, right? Change in momentum of the gas molecules. And due to this change in momentum per unit area, change in momentum per unit area is called what? Per unit time is what? Force. And the force exerted per unit area is called pressure. So in this way, I am going to derive pressure exerted by the gas molecules on the walls of the container, right? For this, you first consider an ideal gas consisting of total n molecules enclosed in this cubical vessel of this volume V. Here, I am considering the motion of one molecule only. There are large number of molecules, n number of molecules. So, I am considering the motion of only one molecule which is moving along the x-axis. This is the area of this phase, right? So, let a small m with the molecule of mass of each molecule, n is number of molecules per unit volume, small n, L is length of side of each cube. So here I am considering the motion of one molecule along x direction. What is the momentum of this molecule moving along the x direction? Let V is x1 is the velocity of this molecule. So mass into velocity moving along x direction, first molecule, so you can write Vx1. Mvx1 is the initial momentum of this molecule, and when it collides with these walls of the container, what happens? It bounces back and there is change in direction, so momentum is what? Minus Mvx1 is the final momentum. So what is the change in momentum? Finally is minus Mvx1 minus initial momentum is Mvx1. So minus 2 Mvx1 is the change in momentum. Now what is the time taken for this collision? T is distance by speed. So it moves and collides with this walls and it bounces back. So total distance covered is L plus L, twice L. So twice L by Vx1 is time taken for this collision. Now force exerted on this wall is how much? Change in momentum by time taken is the force. So change in momentum time taken put these values, you get mvx1 square by L. This is the force exerted by the first molecule. Now force exerted by all the n molecules is how much? You add like this first molecule, in second molecule you take velocity Vx2, third molecule you take velocity Vx3, right? In this way you add all these forces, you get force exerted by all the n molecules. And what is the pressure exerted by all these molecules? Pressure is force per unit area. You divide by area, area is what? L square. And force due to all the n molecules is this one. You divide it by this L square, you get this term. M inside the bracket Vx1 square plus Vx2 square dash 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 plus Vxn square divided by L cube. Right? This is the pressure exerted by all the molecules along x direction. In the same way, you can calculate pressure exerted by all the molecules along y and z axis also. So pressure exerted by all the molecules along y direction is this one, and along z direction is this one, right? Hope it's clear to all of you. So since the gas exerts the same pressure on all the walls of the container, so you can write Px equal to Py plus Pz equal to P. It exerts pressure in all the directions equally, right? So P becomes Px plus Py plus Pz by 3. Total pressure is Px, pressure along due to all the molecules along x direction plus along y direction plus along z direction divided by 3. We put all these values, you get this one, P equal to 1 by 3 inside the bracket m by L cube, and here square bracket V1 square plus V2 square. What is this V1 square? I am writing here V1 square is first molecules moves along x direction, y direction and z direction. This is total velocity. V1 is the total velocity of the first molecule, right? So this Vx1 square plus Vy1 square plus Vz1, so you can write as V1 square. For second molecule along all the direction, I am taking here V2 square, and in this way nth molecules Vn square. Here V1 square is this one, V2 square is this one, and so on, right? So next P equal to 1 by 3 Mn by L cube inside the bracket V1 square plus V2 square dash 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 Vn square divided by n. Here I am multiplying and dividing by capital N. Why? So that this is the velocity of all the molecules along all the directions. So if you divide it by this n total number of molecules, this you get root mean square velocity, right? What is this root mean square? I am telling you after this one. So this v1 square plus v2 square plus v3 square dash 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 divided by n is, you can write as vrms whole square. This vrms is called root mean square velocity. What does it mean? Square root of mean of square of all the velocities, square root of then mean of all the individual velocities, v1 square, v2 square, vt square. This is vrms, root mean square velocity, square root of mean of all the velocities of individual molecules, right? This is called root mean square velocity. So this divided by n is also, yes, right. So this p becomes 1 by 3 m. N is what? This n is number of molecules per unit volume. This is number density. vrms whole square. This is equation number 2, where n is number density, number of molecules per unit volume. This is the expression for pressure exerted by the gas molecules on the walls of the container. This is very, very important relation. P equal to 1 by 3 mn vrms whole square. You can write in terms of total number of molecules also. P equal to 1 by 3 mn by v multiplied by vrms whole square. You can also write this one in terms of density. How you write in terms of density? Yes, you know P is what? 1 by 3 mn by v vrms square. This m into this n is what? M into n. N is total number of molecules and small m is mass of each molecule. So this m into n is total mass of all the molecules. So you can write it as m then v by vrms, and this mass per unit volume is what? Density. You know, na? So you can write P equal to 1 by 3 rho vrms square. This is another form of pressure exerted by the gas molecules. This is in terms of density. This one is in terms of total mass by volume. This is in terms of number density. You must remember all these forms, right? After that, there is kinetic interpretation of temperature. You know, pressure exerted by the gas molecules. How much? P equal to 1 by 3 mn by v vrms square. So you have to write this equation in terms of kinetic energy also, and how it is related with temperature. How this kinetic energy is related with temperature. I am going to derive this one. So you know, you take v this side, P into v is what? If you multiply and divided by 2, because kinetic energy is half mv square. I want half mv square. So you multiply and divide by 2, then 1 by 3 mn v by v vrms square. Right? So this mn is what? This mn is mass of the molecules, right? Yes, this mn is what? Total mass of the molecules. And you take v this side, so pv equal to, you take 2 by 3 1 bracket, and here half m vrms square. You know, half m vrms square is total kinetic energy of n molecules, right? So you can write pv equal to 2 by 3 e. E is half m vrms square. This is total kinetic energy of all the n molecules. So E equal to, E becomes how much? Here E equal to 3 by 2 PV, or you can also write E equal to, is equation, perfect gas equation. PV is nRT. For 1 mole of a gas, PV is equal to RT. So you can write E equal to 3 by 2 RT. This is the expression for kinetic energy of 1 mole of a gas. So you get the final expression for kinetic energy is E equal to 3 by 2 RT. This is the kinetic energy for 1 mole of a gas molecule. For 1 molecule, this is for 1 mole. For 1 molecule, you know, total energy is energy divided by Avogadro number. And when you divide this by Avogadro number, it becomes R by Na is what? R by Na is Kb. Kb is called Boltzmann's constant. We already discussed this one, its value. So this becomes E equal to 3 by 2 kBt, right? So this is the expression for kinetic energy of 1 molecule. This is in terms of R, and this one is in terms of Boltzmann constant K. E equal to 3 by 2 kBt. From both these expressions, it's clear that energy is directly proportional to temperature, right? So if you write You can write it as E1 by E2 equal to T1 by T2. So from here it is clear that kinetic energy is directly proportional to temperature of the gas molecules. Hope it's clear to all of you. After this, next topic is different types of speed. First one is root mean square velocity. What is this? I already told you that it is square root of mean of squares of the velocity of individual gas molecules. VRMS is square root of mean of squares of velocity of all the individual molecules along all the directions, right? This is root mean square velocity, and its formula is just remember this formula. No derivation is required. It is helpful when you solve the numericals. In terms of R, you can write VRMS is root over 3 RT by M, or you can write, you know, PV equal to nRT for 1 mole of a gas. You can write PV equal to RT. So root over 3 PV by M. It means root mean square velocity is directly proportional to root over temperature and inversely proportional to total mass of the gas molecules, right? And it is also directly proportional to pressure, okay, and volume. So in this way you define root mean square velocity. It's very, very important, right? After that, average velocity. What is this? It is arithmetic mean of velocities of different molecules of a gas at a given temperature, and its formula becomes V average equal to under root 8 RT by pi m, or you can write under root 8 kBT by pi small m. Small m is mass of each molecule and capital M is mass of all the molecules. So hope it's clear to all of you. Next topic is, important topic is degree of freedom. What is this degree of freedom and how you find degrees of freedom for different types of gas molecules? It is defined as total number of independent ways in which the particles of the system can absorb energy. In how many different ways a given particle can absorb energy is called degree of freedom. Total number of independent quantities required to completely describe the position and configuration of the system, and its formula is given by F equal to 3n minus k, where n is total number of particles, right? Total number of particles in the system, and k is number of independent relations in which it can absorb energy. What are different independent ways in which the particles of the system can absorb energy? So n is total number of particles, k is number of independent ways. So degrees of freedom F becomes 3n minus k. And it is different for different types of gases. For monatomic gas it is 3, for diatomic gas it is 5, for non-linear triatomic gas it is 6, and for linear triatomic gas it is 7. You can find the value of this degree of freedom for this monodiatomic gas also in this way if you want. For monoatomic gas, n is 1, right? Only one particle. Monatomic means only one particle. And k is 0, number of independent ways in which it can absorb energy, it is 0. So F becomes 1. So 3 into 1 minus 0, it becomes, sorry, when you calculate this one, it becomes 3. Okay. So for monatomic gas, degrees of freedom is 3. One particle may move in x direction, y direction, z direction. It can absorb energy in x direction, y direction and z direction. So right, there are 3 monatomic gas, number of particles is 1 and k is 0. You put these values, F equal to 3n minus k. K is 0 here, n is 1, one particle. So you get 3. There are 3 degrees of freedom for monatomic gas. In the same way, in case of diatomic gas, there are 2 atoms. It means n is 2 and these are held fixed distance by molecular bond. Thus n equal to 2 and k is 1 relation between them. So you get F equal to 5. So for diatomic gas molecule, degree of freedom is 5. In the same way, for triatomic gas molecules, right, for rigid one, how much? Linear triatomic gas molecule is 7. For non-linear triatomic gas molecules, it is 6. So for linear triatomic gas molecules, n is 3 and k is also 3. You put these values, you get 6. So there are 6 degrees of freedom for triatomic gas molecules. In this way, you can find degrees of freedom also. Otherwise, you remember this one. For monatomic gas, it is 3. For diatomic gas it is 5, it's very important, and for non-linear triatomic gas it is 6, for linear triatomic gas it is 7, right? Hope it's clear to all of you. After this, one important law is there, that is law of equipartition of energy, and the basis of this law you have to find specific heat capacity for different types of gas molecules, which is last topic of this chapter. How you define this law of equipartition of energy? It states that for a dynamical system in thermal equilibrium, system is in thermal equilibrium, there is no exchange of heat, the total energy of the system is distributed equally among its various degrees of freedom. Suppose in case of monoatomic gas, there are 3 degrees of freedom. So in all degrees of freedom, this total energy is equally distributed. Total energy of the system is distributed equally among its various degrees of freedom. So the energy associated with each degree of freedom becomes how much per molecule? Half kBT, where kB is Boltzmann's constant. Total energy, you get the expression for total energy as how much? Total energy is weight, you get the expression for total energy as E equal to 3 by 2 kBT. Na? E equal to 3 by 2 is total energy of all the molecules, right? So if the molecule has 3 degrees of freedom, so this total energy is divided in all these 3 degrees of freedom. It means 1 degree of freedom becomes half kBT. This is equipartition of energy. Okay, so it states that for a dynamical system in thermal equilibrium, the total energy of the system is distributed equally among various degrees of freedom, and the energy associated with each degree of freedom per molecule is half kBT, where kB is Boltzmann's constant. No need to derive this one, only this statement is important, only quantitative discussion is there. For example, for a monatomic gas molecule, each molecule has 3 degrees of freedom. So according to kinetic theory of gases, the average kinetic energy of a molecule becomes, it has 3 degrees of freedom, so 3 by 2 kBT. Each degree of freedom has half kBT energy. So it has 3 degrees of freedom, so total kinetic energy of the gases, average kinetic energy becomes 3 by 2 kBT. And on the basis of this law of equipartition of energy, you have to find a specific heat capacity for monoatomic gas, diatomic gas and triatomic gas. Very important this topic also. Okay. So how you derive this one? You know the energy associated with each degree of freedom per molecule according to law of equipartition of energy is how much? Half kBT, right now. So the molecules of a monoatomic gas has how many degrees of freedom? 3 degrees of freedom. So average energy becomes 3 by 2 kBT. And the total internal energy, this one is for average energy of a molecule. Total internal energy of a mole is how much? You have to divide it this by, multiply this by Avogadro number, and Kb into this Na becomes R, right? So it becomes 3 by 2 RT. And for an ideal gas, you know Cv is what? Du by dt. The rate of this change in internal energy with temperature, du by dt. When you differentiate this with temperature, you get 3 by 2 R, Cv. This is Cv is molar specific heat at constant volume. And for ideal gas, Cp minus Cv is what? R. From here you get Cp equal to Cv plus R, you get 5 by 2 R. And the ratio of specific heats of this monatomic gas becomes gamma equal to Cp by Cv. You divide these to 5 by 3, you get 1.67. So in this way, you calculate specific heat capacity for monatomic gas, Cp and Cv, and also ratio of specific heats of these two specific heat capacity, right? In this way, you find for monatomic gas. Next, for diatomic gas also you can find easily. In case of diatomic gas, it has 5 degrees of freedom, 3 translational degree of freedom and 2 rotational. So average energy of a molecule becomes 5 by 2 kBT. Each degree of freedom has energy half kBT. So it has 5 degrees of freedom, energy becomes, total average energy becomes 5 by 2 kBT. This is average energy of a molecule. For total energy of a mole is, you multiply this by Avogadro number, you get 5 by 2 RT. You know Cv is du by dt, it becomes 5 by 2 R, and Cp becomes 7 by 2 R, and divide this to, ratio becomes Cp by Cv becomes 7 by 5 equal to 1 by 4. This is a specific heat capacity of diatomic gases, rigid diatomic gases, right? After this, next one is specific capacities of non-rigid gas molecules. It has 7 degrees of freedom. Okay, it has 7 degrees of freedom. 3 translation, 2 rotation, 2 vibration. So average energy of a molecular temperature T is how much? 1 degree of freedom, half kVt. 7 degrees of freedom becomes 7 by 2 kBt. Total energy of a mole becomes, you multiply by Avogadro number, you get 7 by 2 RT. Okay. So Cv becomes du by dt, it means 7 by 2R, and Cp becomes 9 by 2R. And you get a ratio becomes Cv by Cv 9 by 7, it means 1.28. In this way, you calculate specific heat capacities of monoatomic, diatomic gas also. Okay. Now, last one small topic is, what do you mean by mean free path? Mean free path is what? You know, average distance traveled by a molecule between two successive collisions. This is called mean free path. Average distance traveled by a molecule between any two successive collisions. This is called mean free path. And its value, just remember this formula also. No need to derive this one in terms of this one, in terms of this. Two formulas are there. Mean free path is given by 1 by under root 2 n pi d square, or you can write in terms of Boltzmann constant kBt by root 2 pi d square p, where d is diameter of the molecule, p is pressure of the gas, d is temperature, kb is Boltzmann constant, n is number of atoms per unit volume number density. So on which factors this mean free path depends? It is directly proportional to temperature, inversely proportional to pressure, also inversely proportional to diameter of the molecule, right? And directly proportional to, this lambda is directly proportional to number density. So these factors mean free path depends. In this way you can define mean free path, and this is the formula for mean free path. And this is last topic of this chapter. Okay students, so hope you like this one short series of class 11th physics. If you liked it, then don't forget to subscribe my channel. Okay students, so keep revising, stay tuned with this channel. Thank you.